Hey folks, today we are going to talk about phase change problems. We're going to be doing a lot of math here, so hopefully you're prepared. All right, we're going to be using this chart a lot, so I'm going to be bouncing back and forth into this chart. You should be able to read this chart. You're given over here 3 specific heats. You're given the specific heat of ice, water, and steam, and you're also given from a solid, liquid, and gas for a couple of other things as well. And you should be able to understand that your delta H of fusion is right here, and your delta H of vaporization is here. And you'll notice that these are given in kilojoules per gram. Now, what we did in the podcast was we did kilojoules per mole. In this case, it's given to you as kilojoules per gram, so you don't have to calculate moles. So that's really actually very helpful and saves a couple of steps as you're doing the problem. So you should be able to do it either with kilojoules per gram or kilojoules per mole, depending upon what information and what table you're given. Okay. All right. If you must add 25 kilojoules to raise the temperature of an ice cube from -15 to -10, is it endothermic or an exothermic process? Well, what is happening? The ice cube is absorbing heat. So it's taking heat away from the environment. So since it is absorbing heat, it is endothermic, right? Guys, if you think of a fire as being exothermic, then that's generating heat. Think of an ice cube. It touches your hand. What happens? It doesn't make your hand hot. It makes your hand cold. So as a result, it's removing heat from your hand. So as a result, the ice cube warming up and eventually melting is an endothermic process. All right. So let's go on to this problem. How much heat is required to raise 40 grams of water from 30 to 70 degrees Celsius? Well, if we think of our little chart, and I'm not going to draw this every time, but if we think of our chart, sorry, it goes like that. What are we doing? Well, we're in the liquid phase. We're starting with 30-degree liquid and going to 70-degree liquid. Okay? So to be able to do that, all we have to do is know the specific heat for water. So our specific heat for water as a liquid is 4.18, and it's in joules per gram degree Celsius. So if I do Q equals mc delta T, then my mass here is 40 grams. My C is 4.18. We just saw that on the previous slide. And our temperature change is 40 degrees Celsius, right? Because it's going from 30 to 70. Okay, so if I go and multiply this out, I get 6,668 joules, which is the same as 6.668 kilojoules, if I want to write it that way, and I can write it as 6.7 kilojoules because I only have 2 significant digits in my question, so 2 significant digits in my answer would be just fine. Okay. All right. How much water can be raised from 25 degrees centigrade to 37 degrees centigrade, which is body temperature, by adding the 2,000 kilojoules in Snickers bar? So if you eat a Snickers bar that has 2,000 kilojoules of energy, right, how much water can be raised from 25 degrees to 37 degrees? Well, again, just like we saw in the last one, we're dealing with liquid water the entire time. All right. So what we can do is Q equals mc delta T. Right? Well, the temperature is going up by 25 to 37, so that's 12 degrees Celsius. And our specific heat is 4.18. And the mass of water is what we don't know, because that's what we're trying to figure out. And we don't know, we do know Q, because it's 2,000 kilojoules. Right, well, 2,000 kilojoules is the same as 2 million joules. Now, how come we need to do this in joules? Well, because our Q over here is in joules. So this is 2 million. All right, so now if I take 2 million, so that means I have to solve for M. So if I solve for M, that's Q over C times delta T, which is equal to 2 million, 1, 2, 3, divided by my specific heat, which is 4.18, divided by my change in temperature. My change in temperature is 12 degrees Celsius. Right? And if I do that math, I get 39,872 grams, which is 39.8 or 39.9. Let's see how many, who knows. Sig figs I'm not going to worry about. So we're going to get about 39.87 kilograms. Okay? That's a lot. That's like 100 pounds. That's like a lot. Anyway, okay, so that's a lot of weight. All right, let's go on to number 4. How much heat does it take to melt 65 grams of ice at 0 degrees Celsius? Okay, so now what we're doing here is different. We're just melting 65 grams of ice. The temperature is not changing, but we're melting it. So if we think of our graph that we have, we're talking about ice melting. It is staying at 0 degrees Celsius. Right. So as we look at our numbers, instead of our specific heat, what we want to look for is the heat of fusion. How much energy does it take to melt stuff? And here it says it takes 0.333 kilojoules per gram. You'll notice that there's no change in temperature, right? And there's no change in temperature because the temperature is not changing, so temperature is never mentioned. All right. So we have 0.333 kilojoules per gram. So let's just write that down. 0.333 kilojoules per gram. Right? Well, we have 65 grams. So if we take 0.333 kilojoules, just look at our units per gram, and we multiply by 65 grams. Well, what disappears? Grams disappear. We're left with kilojoules. Right? So that's all we have to do. And we get 21.7 kilojoules. Okay? Now, the other way to do this, if you like, is with our typical way of looking at problems. So I'm going to write it that way as well. We start with 65 grams of ice, right? And if we do it this way, we have a relationship of kilojoules to grams is that 1 gram takes 0.333 kilojoules. So our grams cancel. We're left with kilojoules. And again, doing the math, we get 21.7 kilojoules of energy. So you can do it either way, but that's your answer. All right. Calculate the amount of energy required to change 100 grams of ice at zero, right, to gaseous steam at 100. All right, so let's see, what are we doing here? Let's again think about our little graph. Our little graph looks like that. And what are we starting with? Well, we're starting with 100 grams of solid ice at 0 degrees Celsius. Well, 0 degrees Celsius is here, and because it's ice, we're starting at this point over here, because we have to melt it first, and then we have to heat it up. And then after it's heated, it has to be converted all the way into steam, so we have to go over here. So we have 3 steps. 1, 2, 3. We have 3 steps to get our answers, right? And it warns us to be aware of kilojoules or joules, so how we have to kind of look for that. All right, so let's go and look at what information we have. We have 100 grams of solid ice, so that's what we're doing. We're taking 100 grams of water and converting it. So we're going to have to use our heat of fusion to go from ice to liquid. We're going to have to use our specific heat of water, of liquid water, to go all the way from 0 degrees to 100 degrees Celsius, and then we're going to have to boil off all that stuff using our heat of vaporization. All right, so let's go ahead and do this in 3 steps. Our first step is melting everything. So we're going to start with 100 grams of ice, and we're going to convert from grams. We know that we have a relationship between grams of ice, which is 1 gram of ice, to 1 gram to, sorry, how much energy does it take to turn 1 gram of ice to melt it? Well, that was this 0.33 thing. Notice it's kilojoules per gram. 0.333 kilojoules per gram. So 0.333 kilojoules for 1 gram. All right, that's going to be our first number. I'll do that in a minute. So our second number is what we use for the second number is we are going from 0 degrees up to 100 degrees. So instead of melting, now we're looking at actually changing our temperature. So Q is equal to mc delta T. Right? So we can do our M, which is 100 grams. It hasn't changed. And our specific heat is 4.18. It's over here. And that's joules per gram degree centigrade. So that's 4.18. So I have to multiply by degrees centigrade, which is 100 degrees. Right? And that's going to give me an answer. So that's part 2. Now part 3 is I have to go and I have to do the same thing again. And I have to go and boil everything. So again, I'm going to start with 100 grams now of liquid water. And what do I have to do? Well, I have to convert from 1 gram of water. And how much energy does it take to boil 1 gram of water? Well, I go back to my trusty chart, and my heat of vaporization says it takes 2.26 kilojoules to boil 1 gram of water. So 2.26 kilojoules to boil 1 gram of water. Okay. So what do we finally come up with? Well, our first number is 33.3 kilojoules. Our second number is 41800 joules. And our third number is 226 kilojoules. All right, so I can just add all these numbers up, right? Well, no, I can't. You'll notice that I have kilojoules and kilojoules and joules in the middle. All right, so this guy's going to be a problem. So let's fix that. Let's convert that to kilojoules. So that's 41.8 kilojoules. I just divide that by 1,000, right? So that gives me that number. Okay. Now what I have to do is I have to add all these three things up. I add up the 33.3. I add up the 41.8 because that's now in kilojoules, and I add up the 226. When I add them all up, I get 301.1 kilojoules. That's a lot of heat. All right, let's try our next one. Our next one says calculate the amount of energy released by cooling. Ooh, we're cooling now, right? But that really doesn't matter. By cooling 59 grams of liquid water from 25 to ice at negative 25. So again, I think of my little graph here. And I'm starting at 25 degrees, and I'm going to negative 25 degrees. So I have 3 steps. I have to cool the liquid water till it gets down to 0. And then I have to freeze that liquid water. And then I have to lower that temperature even more. Right? This is kind of like putting ice in your ice cube trays and freezing them. This is exactly what you're doing. Okay? So I have 3 steps. I'm going to cool first, and then I'm going to freeze, and then I'm going to cool the ice. So my first is going from, my step 1 is going from 25 degrees Celsius down to 0. All right? So my delta T is going to be, my delta T is equal to 25 degrees. All right? So I do Q equals mc delta T. So my mass is 59 grams. My specific heat, now we're dealing with water. We're dealing with liquid water. So that's 4.18. So this is 4.18. And my temperature change is 25 degrees. Right? So that's going to give me a number of, let's go ahead and do this, 6166. And because this is Q, this is joules. Because remember, this thing is given in joules per gram degree centigrade. All right, so now let's look at our second piece. Our second piece is 0 degrees, and it's freezing. It's the water freezing. So I have no temperature change at all. So what I have to do is I have to say, well, I've got 59 grams of water, and I want to freeze it. So I have to look up my heat of fusion, which is 0.333. It's the same whether you are melting or freezing, doesn't matter. And notice this is in kilojoules per gram. Sorry, went the wrong way. So that's in kilojoules per gram. So I have to go and get rid of 1 gram of water and go to kilojoules, which is 0.333 kilojoules. And when I do that math, I'm going to get 19.7 kilojoules of energy to go from a liquid to a solid. But I'm not done yet, because now I have to take that solid and I have to continue down until I get to negative 25 degrees. So now I'm going from 0 degrees to negative 25 degrees. All right, so my delta T is again 25 degrees. So my Q is equal to mc delta T. So my M is still the same, it's still 59 grams. And my specific heat is what's different. Now notice here what I've got is I'm cooling off ice. I'm not cooling off water. Water is 4.18, but ice over here is 2.09. So instead of cooling off water, I'm cooling off ice, which has a specific heat of 2.09. So that's 2.09 is my specific heat, and I'm still going down 25 degrees. Right? When I multiply that out, I get 3,083 joules. Nowhere near as much, about half as much as it does when it's liquid, so it's easier to cool it off when it's a solid. All right, now I'll notice I've got joules and joules again. Let's convert everything to kilojoules. So let's make this 6.166 kilojoules. That's 6,000, by the way. Right, and this is 3,000, so we're going to make that 3.083 kilojoules. So I have to add this one, and add the 19.7, and add the 3 point whatever, right? And when I'm all done, I get 28.9 kilojoules to go from positive 25 to negative 25 with the freezing going on in the middle. All right, so how much heat would it take to raise 5 grams of water from negative 50 to 200 degrees Celsius? How many steps does it take? Well, we have to think about our little chart. And we start at negative 50, so that means we have ice. We have an ice cube that's very, very cold. And we're heating it up all the way till it's well above boiling, which is 200 degrees Celsius. So if that's happening, we have 5 steps. We have 1, 2, 3, 4, 5. Now, what are the 5 steps we're going through? Well, the first thing we're doing is we're taking ice, which is at negative 50 degrees, and we're going all the way up to 0 degrees. And so that's the first step we're doing. Then, at 0 degrees, we're melting. So that's our second step. So now we're here. And now what we have to do is heat up water. So our water is going all the way from 0 degrees to 100 degrees, and that's as a liquid. And then our fourth step, we have to boil all that water. So we're still at 100 degrees. We never changed that, but we're boiling. So we're changing state from a liquid to a gas. And then our last step, that happens at 100 degrees Celsius. It says we want to go all the way to 200. So we have 100 degrees Celsius, and we're going all the way to 200 degrees Celsius. Okay, so those are the steps we have to take. Now, I'm going to be pretty lazy. I know that when I'm in a single state, which is 1, 3, or 5, that I say Q equals mc delta T. And I also know that my Q is always in the units of joules. So, when I go and I do this, I'm going to say, what is Q? Well, Q equals mc delta T. So that is equal to my mass, which in our case is 5 grams, and it's going to be 5 grams all the way down here. So since we have the same thing going on in each of these, I will do those first. So we have 5 grams, and what is our specific heat? Well, when we look at our specific heat, we've got 3 specific heats over here, and what we have to do specifically is focus on each one individually. Right now we have ice, and we are taking ice, which has a specific heat of 2.09 joules per gram degree centigrade. So this becomes 2.09 joules per gram degree centigrade. And we want to heat it up, and how far are we going? Well, we're going from negative 50 to 0, so we have to 50 degree temperature change. Okay? Now, if we do exactly the same thing down here, we have 5 grams of water, and here our specific heat for liquid water is 4.18. We should be very familiar with that number. We've used that a lot. So that is 4.18, and we're heating this up 100 degrees. Right? And so that's going to be equal to that amount. And down here, we have 5 grams, And we're doing our specific heat this time for steam. So we go back and look at steam, and our specific heat for steam is 1.7. So that's 1.7, and we have to multiply by 100 degrees because we're going from 100 to 200 degrees, so that's where that number comes from. Okay? So that gives us those pieces of information. Let's stop for a minute and do that math. That's 522.3, and that's joules. And this one is 2090, and that's joules. And this one is 850, and that's joules. All right, so let's do our other two. Well, the other two, we're looking at how much heat does it take to melt 5 grams of ice. Well, we have 5 grams of ice, and what we have to do is look at our relationship between grams and something else. Well, here's what we have. We have our heat of fusion, and our heat of fusion is 0.333 kilojoules per gram. Guys, notice it's kilojoules per gram, not joules. Okay? So it is 0.333 kilojoules for 1 gram. So our grams are going to cancel. We'll be left with kilojoules. All right, let's go ahead and do the other one while we're at it. We have 5 grams here as well. We're going through a phase change, and so for every gram of water, it's going to take some number of kilojoules to boil it. And if we look at what that number of kilojoules is, it's a huge number. In comparison, it's 2.26 kilojoules. So I have to put 2.26 kilojoules up there, right? So we have to go and do that math. Now, when we do these two, we'll notice this is 1.67 kilojoules, and this one is 11.3 kilojoules. All right. So now, what units do we want? Because we've got some in joules and some in kilojoules. Well, kilojoules is the bigger quantity, so let's go ahead and use that. All right. So I'm going to just write everything out here. This is 0.5223 kilojoules. I want to get everything in kilojoules. My next one is 1.67 kilojoules. My next one is 2.090 kilojoules. My next one is 11.3 kilojoules. And my last one is 0.850 kilojoules. What I have to do is add all those up. Okay? When I add all of those up, assuming I did my math right, I come up with 16.4 kilojoules as my final answer. Okay? Long problem, sorry, but that's just what it takes. Okay, let's do our last problem here. How much energy is required to bring 45 grams of benzene from -10 to +70? Ooh, interesting. Benzene, -10, +70. Well, let's hold on for a minute. Let's draw our little graph here, our little chart. Right? And let's figure out where we are. -10 to +70. All right, so -10. We have to look at benzene. Benzene is this one down here. We're going from -10. Well, you'll notice its melting point is 5 degrees. So if we're at -10, that means we're a solid. All right, well, let's look. Let's just draw a melting point, and boiling point is 5 and 80. All right, so this is 5 degrees, and this is 80 degrees. All right, so where are we starting? Well, we're starting at -10, so that means we're down here somewhere, and we're going up to 70, which means we're here. So we haven't boiled yet. So we have 3 steps where we're going as a solid, we're heating up a solid, and we're starting at, let's see, -10, and we're going all the way up to 70 degrees. Right. So the first step we're making is from -10 up to 5 degrees. Then at 5 degrees, we melt. Now, guys, this is not water, it's benzene, so it melts at a different temperature. And then what we have to do is heat that benzene up from 5 degrees to 70 degrees, 5 going up to 70 degrees. So here I have a 15-degree temperature difference, and in the bottom I have a 65-degree temperature difference. So for this we use Q equals mc delta T, and our mass is 45 grams. And what's our C? Well, we have to go look that up. So for solid benzene, our specific heat, these are our specific heats over here. Our specific heat for a solid is 0.55. So our specific heat for solid benzene is 0.55 joules per gram degree centigrade, and our temperature change we said was 15 degrees. Right? And let's do exactly that same thing for the bottom one, MC delta T, because again I'm within one phase. So I still have 45 grams. And here my specific heat, if I look up my specific heat for liquid benzene, it's 0.96. So that's 0.96. And I have a temperature change of 65 degrees. All right, so that's going to give me a number. Remember, these two numbers are in joules. So let's go ahead and do that right now. That's 371.25 joules. And this one down here is going to be 2,808 joules. But here I have a phase change. So I have 45 grams of benzene. Remember, this is the way we do this. We get rid of grams and we go to something. What's it going to be? Well, we have our heat of fusion. Let's see, our heat of fusion is in kilojoules per gram, and it takes 0.1265 kilojoules to melt 1 gram. So 0.1265 kilojoules to melt 1 gram. Right, so when I multiply that out, I get 5.6925 kilojoules. All right, so that's 5.6925, and these are going to be in kilojoules. I'm going to convert everything to kilojoules, which is 0.371.25. Sorry, no point there. 371.25. And my other one is going to be 2.808 kilojoules. These are all kilojoules. So I have to add all of these up. So when I get my final answer, it's going to be 8.9 kilojoules. And that's my final answer. Guys, if you made it here, you've been paying great attention. Thank you. That's the last problem that we have. And if you have questions, please see us in class. We'll be happy to help you. Okay? Take care. Bye-bye.